Greetings, math friends. I had somebody post a comment that they wanted to see me talk about the limit as n goes to infinity of the factorial being convergent to the square root of 2 pi. And as I considered this, I thought, well, an approach that I might try would be to use a pi function and show the continuation of factorial and where that goes from there. Then I noticed how many different pi functions that we have defined in mathematics over time in different places for different purposes. So I decided that maybe it would be better for me to talk about a disambiguation of the pi function first and then talk about this. And then I decided that I would just talk about pi functions and I would let Bry the math guy talk to you about this. I want to leave a link to his video in the description. Hopefully it will be persistent where you will be able to watch him discuss how to do an infinite factorial converging to the square root of pi. I think as some of us think about this logically, this is kind of in the same frame of idea as adding up all of the integer values and getting -1/12. We're multiplying a whole bunch of values and getting a specific real number. Ordinarily, we would just take these to be divergent, whether it's a series or a product. We naturally take these to be divergent. So there's some kind of situation where we are doing things slightly different to get something convergent. So I'm not going to take that route today. I would like to talk about the pi function, or actually the pi functions. The first pi function that I would like to talk about is commonly known as the rectangle function. And I had actually borrowed this book, interlibrary, through our university library to study the Heaviside function. And it also happens to have the rectangle function in it. This has the rectangle function in it because the rectangle function is important in the study of the convergence of the Fourier series. So this ended up being a really nice book. It had multiple topics that I was interested in. This is published by McGraw Hill, and I'm going to have to return it soon, but I did really enjoy this book, what little of it that I did actually look at. But we get to talk about the rectangle function now. So if we look at the rectangle function of unit height with unit width, we get this piecewise definition for this function. And then I put a little graph together there using PGF plots and TXE, using LaTeX. This is an integral function, so I just integrated from -1.5 to +1.5, and we see that this is 1. We could have tightened those limits up, and then we can expand those limits as far as we want as well. We're still going to get 1 out of this, and that's really what we are looking to get out of this. Is at this point, the way we've defined it, we want an area of 1 under the curve that is above the axis. There's another way that we can notate this function besides pi of x. We could have also called it rect of x. And then there's other names besides rectangle function that this could be known as. It could be the gate function, the window function, or the boxcar function. The gate function could be in the context of if we are doing a certain procedure where we are trying to gate a function. And then we can also do transforms on this function like we would do transforms on other functions. So we can multiply by a scalar. We can adjust inside by addition or subtraction and division. Change the look of this. A quote from Bracewell's book, which I showed earlier, is that it is important in the theory of convergence of Fourier series, where it is generally known as Dirichlet's discontinuous factor. And then my primary reference as we talk about the square function is this book by Bracewell. The next function that we're going to talk about is also a pi function. This one is denoted with a lowercase pi this time, but it's still a pi function, and this one is coming at us from number theory. For this reference, I used Professor Carl Dieter Chrisman's website. We have this pi function defined for values larger than 3, and this is a series. And when we plug in integer values larger than 3 here, we will be able to know how many primes that is less than or equal to the number that we are plugging in here. So you can see as an example here, I did a calculation by hand, and you can see how long this takes. So it would be great if you know some programming to be able to put some code together and automate this so that you're not doing this by hand. And then you see in the lower right hand corner, just by brute force, we can count up how many primes are 7 or less, and we find out that there is 4, which is what we got as the return from our pi function series here. So just kind of wrote this out as the brute force algorithm or the brute force function. The value we put in is we want to know how many primes there are, and I just listed all of those primes, which there are 4. This is easy to do, but if you had chosen a larger value like 103, how many primes would be 103 and below? And then how long would that take you to use this pi function to calculate by hand? Probably going to be a while. Maybe an extra credit project. Consult your instructor in mathematics about that. And then the next pi function that we are going to talk about is the extension of the factorial. So factorial is usually introduced as an idea that we have one input, say 3, and then we are going to take that number, subtract 1, and multiply by that result, subtract 1, multiply by that result, until you get to the number 1, and then you stop, and you're going to do that product. So we have 3 times 2 times 1 is 6. But then people naturally want to ask the question, well, can we get values in between here? So could we do 2.5? Well, we need a factorial extension for that to be able to get those real values between the integer values, and that's where we have a variety of options to do that. One of them is this pi function. As I was studying, I came across a really interesting article that was published on a government website. It looks like it's used with permission of Springer, so it was probably published through a Springer publication somewhere. This is by Ashwani K, Thukral, and they've posted an extensive paper about a lot of information surrounding factorials and extensions and what is available and starts to talk about historically how this was developed, and I was able to follow some references from there as I studied this. Wallace used this expression for sine x, which is a product. This is product notation. It goes well with the video since we're talking about pi functions. This isn't really a pi function, but it does use capital Pi here for product notation, and it also includes the number pi in the formula. Wallace used pi halves here. So this is radian measure. So we have the sine of pi halves is equal to pi halves, the product from n equals 1 to infinity, and we have 1 minus pi halves squared over pi squared n squared. And then we have to go through the simplification process. Sine of pi halves is just 1. If we bring this scalar to the other side, this is going to be times 2 over pi. And then inside here, we're going to square this, and then we have to simplify this fraction a little bit. We have a compound fraction. We're going to have pi squared over 4 pi square n square. And then here we see that this pi square and this pi square are going to cancel. Then we're going to need to get, we're going to subtract this fraction from 1. We're going to turn the 1 into a fraction with common denominator. If we combine the 4 and the n here and rewrite 4 as 2 to the second power, we can put this all in parentheses here to the second power, and doing the same over here with the 1 for common denominators, we're going to end up with 2n squared minus 1 over 2n squared. And that's all equal to 2 pi. We're going to use the difference of squares here to split that into 2 pieces. We're also going to take the reciprocal of both sides. Since this is 2 fractions, essentially it's equal proportions. We can flip both sides. So this gives us that we have pi halves is the product of 2n squared divided by 2n minus 1, 2n plus 1. And then we can start plugging values in for this. So I'm going to get in the numerator here, I'm going to have 2 times 2 times 4 times 4 times 6. And what we end up with is we get the even integers doubled up here in the numerator. And other than having 1 here, we have a similar pattern in the denominator. We get the odd integers that are showing up in doubles here, and this is all pi halves. So this is Wallace's formula. If you go through and look at Euler's calculations for his delta function, which again becomes known to us here in modern times as one of our pi functions, you see that it's very similar. We have this almost going on under the square root, and then over here we end up with the square root of pi over 2. How does that happen? One of the first things that we can do is we can take one of the 2's to the other side. So I'm going to divide a 2 out on both sides. All right, now once I have that, I take the square root of both sides. And this is going to give me the square root of pi divided by 2 is equal to the square root of all of this. And that's really the easiest way for me to make sense of how Euler was able to take this thing and get that it has a convergence to the square root of pi over 2. Well, I can follow Wallace from the definition of sine x to his product getting to pi halves, and then I can do the algebraic manipulation so that I match Euler's work here, and from Wallace's work I know that this is in fact the correct answer. You can dig into Euler's work and look at what he wrote in arriving at this point, but he was actually calculating the delta of 1/2, which is what we would say is 1/2 factorial. So again, he was working with what would become known to us as a pi function, which is a factorial extension in this case, this particular pi function. So he came up with the square root of pi over 2 is 1/2 factorial. Going back to this pi function, which is the one I originally started to work with as an extension of the factorial, if we want to take the limit as x approaches infinity of pi of x using this definition, you can work through the integration process here. It's not the most pleasant work through in my opinion. We're going to get something of the idea, and some of you may not like my integration process here. We end up with the first step out going here. We're generating an integral over here that's very similar to the original, only we have the scalar x out here now, and then we have x minus 1 here, and then we have to look at this and essentially go through the same process. So we generate another one of these and another one of these, and the process continues to go on. And then, of course, we are doing this as a limit as x is going to approach infinity of all of this. Eventually, what it works down to is you basically generate the thing that you would expect to generate. At least this is what I came up with. And this is essentially the definition that we would expect for the normal factorial that you first get introduced to, that it's this value minus 1, minus 1, minus 1, until you get down to 1, and then you take the product of all of those. So this is not really insightful on how you would get the idea of this being going out to infinity. I don't know. You're not going to see a convergence here. This not converging didn't lead me to a new insight, other than kind of seeing that this really does shake out to be kind of the traditional factorial definition if we think about these as just integer values. I'm going to again refer you over to Bry the Math Guy, and you can watch his video on his explanation of how we get a factorial extension in such a way that we can find a convergence. And not everybody's going to be happy with that explanation, but it is the common explanation I think that you're going to find if you're going to attempt to find convergence from taking the limit as x is approaching infinity for the factorial. I found it interesting to look at a variety of different ways that we have defined pi functions over the years, and these come from various places. That's one of the things about mathematics, that sometimes we see notation that is used in different places in mathematics. They mean different things, so you really have to understand the context. So if somebody tells you to use a pi function, you really have to know the context of it. Are you doing something with a Fourier series? Are you doing some kind of number theory? If you're doing number theory, are you looking at primes, or are you looking at factorials? The number pi, when we discuss Euler, is not even used consistently by Euler. It wasn't a constant to Euler. It represented ratios of parts of a circle. In common notation now, it is the ratio of the circumference to diameter of the circle. But if you study Euler's original writings, you're going to see that's not how he always used it, though in this particular context, that's the way he used it. Hopefully this has been interesting to you. Mathematics is really a deep ocean of ideas. Hopefully you can find some mathematics in your part of the world to enjoy and share with others. Cheerful Calculations.